Okay, so we have 4 lectures left in this course, 2 this week and 2 next week. And finally, as it were, finally, we get some really interesting results from much of the formalism we have developed. And what I'll do today is I'll start by doing something which I should have done long ago, but I didn't, and that is defining what is an asymptotically flat space-time. You might think it's obvious, it's just a space-time which at infinity is flat, but as usual in GR, that's easier said than done. We need to do a little work to define the concept. Wald's book has an entire chapter. I'll give you a simplified explanation of what asymptotically flat space-time means. The reason we are doing this is that we will be proving theorems which are quite general about black holes, trapped surfaces, presence of singularities. We also have a conjectures on cosmic censorship. We'll prove that black holes cannot split but they can join. We'll prove that the area of a black hole always increases. We'll prove that surface gravity in a collapsing, in a black hole formed from collapse is constant, and in this way we will have all the laws of black hole thermodynamics. But all those laws are derived for asymptotically flat spacetimes, and I'm sure there are some counterparts in other spacetimes, but issues become more complicated, and when the legendary textbooks of Wald and before that Hawking Ellis were written, it wasn't clear whether we do have a cosmological constant, so it was quite reasonable to think maybe we live in such a spacetime. Today that doesn't look so likely. Okay, so obviously the intuitive notion is that it looks like Minkowski sufficiently far away. You can surely prevent that by having some matter distribution which doesn't die off far away. If you can make some magic distribution of matter which never dies off, then of course you can prevent this happening. So obviously your matter distributions and everything, gravitational fields, should all be sort of localized. But one has to be a little careful, and that's because far away is the real tricky question. What does far away mean? In a space-time or in a non-compact space-time, far away means is somewhere where we reach as a limit, but it's not actually a place. It's not somewhere we can actually go. Also, far away is a limit. And there's another fact which we saw by considering the conformal compactification, which we'll be using extensively, which is that Minkowski has 3 different types of asymptotic regions, all of which can be called far away. So one is time-like future and null infinity, I plus minus. One is space-like infinity, I 0. And then there is null infinity. So what are we going to insist that the space-time should do. Should it look like Minkowski near all of these limits? And if so, how do we impose the limits? There are two different questions. You can guess that the answer of how do we take the limit is that we use the conformal compactification, which formed the basis of Penrose's idea of Penrose diagrams. Because the whole point of conformal compactification is that these infinite points come to a finite distance by removing a conformal factor, and then at least we can include them in the space-time, get an extended space-time, though it's not the physical one, and then we can do things there, and then we can transport our results back to the physical space-time because the causal structure of the conformally compactified and the physical space-time is preserved. So whatever we say about causality will be true in both. Okay. Now the first observation is that I plus of all of these points, I plus and minus are problematic. And let's try to see why in a picture. So for Minkowski we have this kind of structure where I0 is here, I plus is here, I minus is here, and square I plus and square minus are here. Now the problem is that if there is some matter distribution which was there in the far past, then it can make it problematic to access I minus, because you want to be outside that. Similarly for matter distribution in the far future. And the reason why the eyes are affected and not these other things is that it's only a time-like object which can be kept at rest and just allowed to linger there. So the matter distribution can just be there for all time in the past or all time in the future. An example of that in fact happens when we have black hole formation, where we sort of think of the matter as being some spherical shell and eventually it forms a horizon. So we simply exclude them. We don't require an asymptotically flat space-time to have an I plus minus, but it can have if it wants. We don't require it. But we do require I0 and square plus minus. So that's the first observation, that out of three types of infinities, the time-like one is not required, the other two are required. Now we have to deal with the actual process of making this requirement, and depending who you read, there are several conditions, and I have filtered out what I think are the essential conditions for an asymptotically flat space-time. So definition and asymptotically flat space-time, and I'll denote a space-time by giving you the manifold as a topological and differentiable object, and then next to it writing the metric, is said to be asymptotically flat if there exists a conformal compactification. I'll probably start using CC as a short form. This is also called unphysical space-time by many people, including Wald. And for a conformal compactification, I write M tilde and the metric G tilde. And then I'm going to write several conditions, 6 conditions actually, which have to be all satisfied for the manifold to be called asymptotically flat. And one comment which is not completely obvious but and it's a little tricky. Okay, so we have M here and G. These are the true space-time and the true metric. We have a different space-time and a different metric. Now it's easier to ask what's the difference between these two metrics, and you know the answer, that G mu nu is equal to some conformal factor squared times G mu nu tilde. So this is what tells me the difference between G and G tilde. It's a different metric. Okay. What is M tilde? Is M as a topological space plus the boundary points, and this is in okay, and this can be done that you can add these boundary points once you have gone to G tilde, because now they are at finite distance and you can just include them into M tilde. Include them into M, and as a result you get M tilde. So one subtle point here probably is that we can talk of the original space-time with the new metric also. How? Well, M is a subset of M tilde, the part which doesn't have the boundary points, and on that I can impose this metric, which is a different metric from the physical one. Okay? Technically, people make a conformal map from M into M tilde, which, so it's the image of some map of M which becomes a subspace of M tilde, but you can just intuitively think of M as being a submanifold of M tilde, and we'll be using that sometimes. So that means that with M I can have two metrics, either the metric G or the metric G tilde, but with M tilde I use the metric G tilde. M tilde doesn't make sense in the metric G, because in the metric G those boundary points are not there and they are crucial in the what M tilde means. Okay.
M tilde will be well defined without a metric. We don't need. We can add the boundary points. It's a well defined manifold. It's just that what we're doing will need a metric. So that is why we need to.
Yeah, but actually adding the boundary points, I think the problem is, yeah, in principle it should be so, but this little bit goes to the point of, you know, when we define a manifold, we often define it using a metric. And M tilde is defined by saying that in the metric G tilde there are these points and you add them. So yeah, maybe in a very abstract sense that may be true, but we'll never use M tilde with the metric G, but we will use M tilde with the metric G tilde and also M sitting inside M tilde with the metric G tilde. And the reason is that ultimately we want statements about this and not about this. Okay. So one is that T mu nu, the energy momentum tensor, goes to 0 at sky plus or minus and I0. Now to be very precise, I should tell you how fast it goes to 0. I'm just going to skip that. So there are some formulations, it will just add a lot more to this discussion to say how fast. So T mu nu can be of course already 0 if we want, but that's too special. So but at least near these boundary points it should go to 0. Okay. By the way, these properties are all properties of this M tilde G tilde, not of M and G. Therefore they are very precisely defined. Okay. The second property is that I can take M tilde and I can remove from it M. So that symbol means minus or subtract it, and in the sense that M is a subset of M tilde as I just explained, and the result should be what? It should be J plus of I0 union J minus of I0 and the closure of that. Okay, so the causal future and past of I0 and closure which ensures that basically all of scry plus, scry minus and I0 are in that make up that difference. So the boundary is really what I said it should be. And here you can see that I plus and minus don't enter. Okay. So you can also think of this as I0 union square plus union square minus. Then 3, the space-time is strongly caused, the space-time which is I guess M tilde, well, no, let me see now, it should be M or M tilde, open neighborhood of, my notation isn't very good. Yeah, it probably doesn't matter. M and M tilde are both strongly causal together. So we'll just write M tilde is strongly causal in a neighborhood. Of its boundary, which is what I've written about. Neighborhood of this. So in pictures, if you think of this structure, so I0 and sky plus and sky minus should be there, should be the boundary. And the idea is that supposing I come in from the boundary, either in towards the future from the past or this way, or even this way from I0. So imagine some shaded region like this. It's not on the boundary, but it's not deep inside. It's just some sufficiently small region near the boundary. Then the space-time should be strongly causal there, because then you will have prevented some class of, you can also use stably causal, which is a little more, a little stronger. So you would have prevented odd things like a future directed curve somehow going into sky minus, or a past directed curve going into sky plus. So this strong causality is assumed. We won't be using everything in detail, but I think it's good to list list all the conditions. So this metric G tilde is smooth. Smooth means infinitely differentiable. Also, sorry, G tilde and omega. Omega is the conformal factor between in that box over there, which relates G and G tilde, are both smooth. Everywhere except possibly I0. So I0 is a problematic place, and I'll in a couple of minutes I'll explain what is the problem to have things being smooth at I0. Let me come back to that. And so there are some weaker requirements which I'll state for I0. 5. Omega vanishes on sky plus and minus. Remember, this is the property that allowed us to conformally compactify. The fact that omega vanishes, we took out a vanishing factor, and that's how we were able to get a metric which brought the infinity into a finite region. So it vanishes, but its gradient should not. So we'll write this gradient in the tilde metric, but if this doesn't vanish, then the gradient in the original metric also will not. So this condition tells you that you can come in. So the conformal factor starts to be non-zero as you come in. That's the intuitive reasoning. And 6. Scribe plus and minus are complete, which I have to explain in a second. So that's all. So it's quite a lot of stuff that makes up an asymptotically flat space-time. I think 1, 2, 3 and are reasonable. 4 I'm about to explain, and 6 I'll explain. I think 5 is also reasonable. So problem with I naught is that in a Penrose diagram it's actually a point, okay? But space-like infinity is surely not a point, it's a d minus 2 sphere, okay? And the point is that I can approach I naught going through different angular directions. The Penrose diagram only shows me the radial direction and the time direction. Of course, the time direction is sort of, at least in Minkowski, it's clear that is just one direction. But the radial direction is some kind of average of d minus 1 space directions. It's square root of sum of all of them. And there are d minus 2 different angles. Okay? And so when I go towards I0, I'm free to go there from all possible angles. And depending on which one I choose, I land in a different part of real space-time, right? Literally, if I go there or there or there or there, I land in different places. But on the Penrose diagram, I get bunched up all into a single point. You may argue that even I plus and I minus have that property, but for a different reason. I plus and I minus are the origin of spherical polar coordinates. So the fact that there is a single point there is just the breakdown of spherical polar coordinates. But I0 is not like that, it's far away, but it's somehow averaging over a lot of directions. So can land on it from different directions. But since it's a single point, the metric, for example, g tilde mu nu, will have a fixed value there. Okay? But now, what can happen is that if I go in along one direction and come out along another direction, that value might not change smoothly. So therefore, g tilde is taken only to be continuous, not necessarily differentiable. So it doesn't jump. But as I go in and out, the derivative of g, the variation of g might just not be smoothly matched on. And in fact, there's a more complicated condition called c greater, you know that c infinity means differentiable, and there's something called c greater than 0, which is used by, c0 means continuous, c1 means once differentiable, c greater than 0 is something which I think Wald has invented, or maybe Hawking. It has some more stuff in it, but you know, if we keep going on with that, we'll need at least 6 lectures to cover asymptotically flat space-times. So I'll just leave it at this, that because I0, I think it's important physically that I0 is a weird place. We don't go there because it is space-like infinity, but it belongs in our manifold M tilde, and we should accept the weirdness of this point. For the same reason, the conformal factor also can have somewhat non-standard behavior, but actually it turns out that omega is differentiable, but maybe once or twice, not more. So this is point 4. Small explanation of point 4, and then point 6. Okay. Point 5 actually. Well, maybe not 0.5, but a combination of 5 and all the others allows us to choose a coordinate system such that the metric goes to, well, Minkowski metric plus order 1 by R. This is what we were trying to achieve in the first place. And in particular, we often like to take the combination of T and X, rather actually T and R, which is the U or V, the ingoing or outgoing. And what we always do with sky plus and minus is to have coordinate U go that way and V go this way. Okay, so when I say we choose coordinates T and X, it's the same as saying I choose U, V and thetas, or U, R and thetas, or V, R and thetas, and Eddington-Finkelstein. Those are all related in ways which we have already learnt. But the point is that complete, I plus minus are complete once we have chosen this, is the statement that U actually and V both actually range from minus to plus infinity. They don't suddenly come to an end. Okay? Until now we just said that there should be a scry plus and a scry minus. But what does that scry plus and scry minus for an arbitrary space-time actually look like? It should look like, with a choice of coordinates which is Minkowski plus corrections, it should look such that U and V really look like the scry plus and minus of Minkowski space-time, which doesn't abruptly end anywhere. So that is the requirement of that is requirement 6. Now both Wald's book and Rial's notes have pages and pages of calculations explaining how to implement various of these conditions, and I'm not going to do any of that because it would just take way too much time, and actually because for the conceptual things we are doing, it's probably not needed to know everything. Okay, so now with this we can get on to a new topic, which is we'll use these, at least we'll use the existence of this criterion, asymptotically flat, and now we can talk of generic, but of course asymptotically flat black holes and cosmic censorship. And here we face the following question. Yes?
So this, the y factor may, the derivative of the y factor may vanish perpendicular to y plus y.
Should not vanish actually, because we want the conformal, the y factor to start being, see, it will be very special if it has many derivatives vanishing at the boundary. Then in lowest order the metric will still be, how to say, actually, okay, yeah, actually I don't know exactly what goes wrong, but intuitively I would say that you want the conformal factor to tend to 0 only on the boundary and not faster than the minimum.
Okay, no, I was thinking that the condition should not be on arbitrary, on the derivative in general, but only a component along I plus.
Oh, that way.
Normal to I.
That way.
Normal
That might be true. That might be true. I don't think that's what it said, but that might be true. You're asking why didn't I say gradient only normal to the boundary? Yeah, well, normal will be difficult to say because actually boundary is null, so normal will be in the boundary. So this will be in some linearly independent direction. Yeah, actually it's implicit because we've said that omega is 0 everywhere on the boundary, right? So its gradient along the boundary is certainly 0 anyway. So I think this is the only thing it can, given that it's 0 along a line, the only thing where its gradient can be non-zero is the direction which is away from the line.
And one more thing, so even before we start mentioning any of the conditions, we should already have a notion of I plus I0 and I minus, right?
Yes.
So should we be saying that the boundary of M tilde is already homeomorphic to the boundary of conformally compactified Minkowski space.
Yes, that's what this says, right? Doesn't it say so? I thought the first three conditions basically say that. The first two conditions.
I plus minus and I.
Ah, okay. Okay. Well,
So, like for example, d theta will not happen.
yeah, but this, of course, we are defining asymptotically flat, right?
Yes.
So that we,
Yeah, sure.
so de Sitter will not have it, of course. Maybe I could have written them in a better order. I see that you're saying that I require my. Yeah, I think there's one more step which I could have said. I think it's enough if I require I0 to be there, because then J plus, whatever is J plus of I0 minus I0 itself, that is Scri plus. So there's actually a definition of Scri plus and Scri minus which I skipped. I'll probably add that back with my notes. Okay. So now we come to the question, what can we extract from our lessons regarding Schwarzschild? And well, if we had a few more months, we would have also done Reissner-Nordstrom and Kerr black holes and Kerr-Newman black holes. We would have accumulated a lot of lessons about black holes. But a lesson is just a lesson because, well, in the case of Kerr, it's a vacuum solution, so Schwarzschild a vacuum solution. But maybe we want to study non-vacuum solutions, collapsing shells, some stress energy and all that. And there should be a general concept that what is a black hole in general. We just can't say anything which looks like Schwarzschild. We need to give a definition. And whatever that definition, so the key question is what is a black hole? How do we define a black hole? And that's actually quite straightforward, and we'll do it in a second. And as you can guess, the lesson we are going to learn is that it should have an exterior, an interior, and a boundary of the interior, which we'll call the event horizon. So these are the three qualities, and we'll write that down. So that's one thing. The second thing is there's going to be an exterior, as I said. So exterior should not have singularities. Now in Schwarzschild that's true because the singularity is at r equals 0 and that's the end of it. It's much less than r equals 2 gm, which is the event horizon. So the exterior is free of singularities. But one of the burning questions is what tells us that other classical solutions of Einstein equations don't have singularities in their exterior region, however we define it. So here we have a conjecture or a set of conjectures called cosmic censorship conjectures. And I've been trying to collect different people's versions of the conjectures and I have not completely done. So the formal statement of both the weak and strong cosmic censorship I'll give you tomorrow. But let's make some little comments, just maybe time pass comments about it. It seems like at first it's something you should be able to prove. General relativity has a Lagrangian. Using that Lagrangian, prove that cosmic censorship holds in some form. Assume whatever you want about the space-time other than actual absence of singularities, and prove that whenever there is a singularity, it is inside the black hole region of that space-time. Some space-times which are not black holes don't have a black hole region. So you should be able to prove it, cosmic censorship. Well, that hasn't happened. And as far as the formalism of GR, it looks like maybe it is not possible to prove. I don't have a deep understanding of that. However, there are two interesting inputs into this question. One is a theoretical input, which is that even though analytically nobody proves that singularities are absent outside in the exterior, people are doing numerical simulations of gravity, and numerical simulations have not led to any situation where something reasonable, some reasonable matter distribution went and formed a visible naked singularity. So you could say that some sort of evidence, because we don't assume in those numerical simulations that there are any symmetries or simple spacetimes. We do it in quite generic cases, and failures of cosmic censorship should show up if they are there, and they don't show up. Secondly, experiment. So in 1972, Penrose speculated that when two black holes collide, that the result might be a naked singularity. Now this would send LIGO into complete chaos, because then they would actually be not chaos, actually a very positive kind of chaos. It would be much more exciting than seeing just gravitational waves, because then we would know what is the physics of a naked singularity. But everything that LIGO has seen is consistent with the fact that when two black holes merge, all you get is another black hole. They can even estimate what is the size and angular momentum of the merging black holes and the result of the merger, and everything is consistent with the reasonable idea that singularities simply don't come out of the black hole. They are carefully hidden, and when two black holes merge, whatever was singular inside them just merges into a thing which is singular in the merged result. So, no evidence to the contrary. And instead, supporting evidence numerical simulations, no singularities. You should say numerical simulations of realistic things, actual observation. When I say singularity, I always mean an observable singularity, which is exactly what would violate cosmic censorship. Okay. Now, one reason that I will give you the definition of the statement of cosmic censorship hypothesis is that these are hypotheses about initial conditions not evolving into something which has singularities. So we need to talk about initial conditions. That's also a whole chapter of Wald's book, which I haven't even discussed. And we need to talk about Cauchy development from initial conditions and all that. So some formulation of that I'll give you tomorrow. But what you can do is, supposing you have a space-time, you should at least be able to define in that space-time what are the properties which would prevent it having singularities outside. So this is the, if you like, intuitive part of the discussion, and now we'll write some definitions and then eventually prove a couple of theorems. So when it comes to definitions, the first question to ask is, let's ask what is the exterior of a black hole space-time? Okay, or we can say what is the exterior of any space-time. If it's not a black hole space-time, maybe that exterior will be just the whole space-time. And the most reasonable definition of exterior is J minus of Scri plus. we first go to we are working in the conformal compactification, we go to Scri plus, and then we ask what signals can reach there. Okay, so we go back along those signals, and everything that we get to is a region from where signals can reach Scri plus. And by assumption, our space-time is asymptotically flat, so there is a Scri plus. The region from where signals can reach it should be called the exterior region. If it's the whole space-time, well and good. Minkowski, that's what it is. But if it's Rothschild, then it's only the region outside. So it fits. So just to be a little more precise, so this is still an intuitive statement, precise definition. The exterior of an asymptotically flat space-time m g mu nu. Actually, g mu nu doesn't play much role in this. So let's call it m. Is m intersection j minus, little more precise than what I wrote before. J minus of Scri plus. So whatever is in m, so Scri plus itself is not in m, it's in m tilde, I0 also similarly. So it's whatever of j minus of Scri plus lies in m, that's the defined to be the exterior. Once we have that, then we can define the black hole region, which will come up repeatedly, and therefore we give it a name of m, denoted, I'll call it curly B. Some references use ordinary B. Is just m minus m intersection j minus of Scri plus. Okay, now one interesting thing is that j minus of Scri plus, remember Scri plus is the region between I0 and I plus, but it doesn't contain its ends. And so j minus of Scri plus doesn't actually contain the horizon. Okay, in fact we'll be showing in a few minutes that j minus of Scri plus is an open set. Okay, so that means that this black hole region contains the horizon. So the horizon and the what we call interior is all in black hole region. I'll write it in a minute. And the event horizon is the boundary of the black hole region. And we'll use the terminology H for it. Okay. So obviously, if B is non-empty, then we'll say that this spacetime contains a black hole. If B is empty, then spacetime doesn't. Okay. Then there are some nice things we can prove here. One of them is that nice result. It's quite important actually. You can call it a theorem if you like, but it's quite simple to prove. If there's a point P in the black hole region, then the entire causal future of P must continue to be in the black hole region. Certainly in Schwarzschild that was true, but the way to argue this is, suppose the contrary. So then there is some point Q in J plus of P, which is not in B, then of course it's in the exterior. So I don't know what's the best way to draw this, but maybe it doesn't need to be drawn. So somehow Q in the future of P, which is inside the black hole region, Q is outside, okay? But that means that J minus of Q is not fully in the exterior, because P is in it and P is in the interior in the black hole region. So J minus of Q is not fully in the exterior, though Q is. Okay. Now what is the exterior? It's J minus of Scri plus. Okay. So everything that's in the past of whatever is in the exterior must remain in the exterior. So this is a contradiction. If J minus of Q is not in the exterior, that contradicts the definition of exterior. You can go into more detail to state how this works, but I think this is enough. And so we proved the theorem that if a point is in B, then its future is in B, and that also can be extended to a set, which is a subset of B, then the future of that subset is also in B. Okay, good. For Schwarzschild, of course, it's very clear. So exterior is R greater than 2gm, B is R less than or equal to 2gm, and H is R equals 2gm in Schwarzschild coordinates. Okay. And also singularity is at R equals 0. So cosmic censorship holds for this solution. Singularity is not contained in the R greater than 2gm region. Okay. Now there is a property which is defined, which is the basis of the cosmic censorship conjectures, and that property is very nice, and we'll define it now and talk about it. In a way, it's all we need to prove the theorems of interest to us, because as I said, the cosmic censorship conjectures are more about formation of singularities, while this property is about existence or presence of singularities in the full space-time. So it's the difference between emphasizing the formation or the development of the space-time from an initial value surface and just looking at the space-time. So now in this definition, we actually denote the space-time by M and its metric, and the condition we are going to define is called as strongly asymptotically predictable. If it will be strongly asymptotically predictable if the conformal compactification has certain properties. And the property is that this contains an open set which I'll call O tilde, such that 1 O tilde viewed as a space-time by itself with the metric G mu nu tilde is globally hyperbolic. and 2, O tilde contains M intersection J minus of I plus, which, as you remember, was what we call the exterior. In fact, it should contain the closure. So this thing includes plus its limit points. And here, for example, you can see that we are using M, the concept that M is a subset of M tilde, which I mentioned earlier, because we are saying M intersection something is contained in O tilde, which itself is in M tilde. Okay. So let's try to understand the reason for these two properties. First of all, global hyperbolic. Of course, if O tilde, this open set which exists, if it is globally hyperbolic, then obviously it has a Cauchy hypersurface. And now we haven't discussed actually very much what are Cauchy hypersurfaces in generic spacetimes. But now it's not totally generic, it's generic but asymptotically flat. And in asymptotically flat, there is an I0 which we identified. And I0 is a very good point because it's the point between scri plus and scri minus. So if you choose your Cauchy surface, of course you can choose it anywhere you like, but if you choose it to pass through I0, then you have the advantage that scri plus is always in the future and scri plus is always in the past. So the idea is to choose, so we don't know what the spacetime is doing here, but we'll take a Cauchy surface that goes through I0.
Cauchy surface has to go through I0.
Has to go through I0. Why is that actually? Yeah, maybe you're right, but why is that?
Otherwise, you can define a region, you cannot connect it to the Cauchy surface.
Yeah, I think you're right, and actually that I think has also to do with the fact that space-like infinity is shrunk to a point. So yeah, you're right. Actually, that's the only thing it can do, because otherwise it would have actually reached one of future or past null infinity. Can't be correct, absolutely correct. So the Cauchy surface passes through I0, and this exists for this open set O, but if it exists for O, so if, and that's given by the global hyperbolic condition 1 above. So that gives us a series of implications. Since O contains this, no, actually we don't use that at this stage. If it exists for O, it also exists for M intersection O with the metric G tilde, right? Because whatever is this set O, which has a Cauchy surface, I simply look for the points in that O which are in the manifold M, and then of course it will be a Cauchy surface. So if you shrink, if you take a manifold and some part of it by intersecting, then that part will also have a Cauchy surface, so that's fine. Now I claim that this again makes the Cauchy surface exist for M intersection O tilde and the metric G. Here we use the fact that the causal structure of a metric G tilde and G, because of conformal factor, is the same. And therefore it will exist for us. Okay. So therefore, region of M lying in this set is globally hyperbolic. So that's good. Now let's see what condition 2 tells us. Condition 2 says that O contains that, and therefore, so 1 implies this, implies all these. 2 implies that I should find a notation. Nobody seems to have a notation for this space, which we use all the time, the exterior. So this is also globally hyperbolic. By condition 2, it says that it's contained inside O. Now all inextendable causal curves in a globally hyperbolic spacetime intersect a Cauchy hypersurface. So there cannot be a naked singularity in the exterior region under this condition. So strongly asymptotically predictable is like a diagnostic of a space-time without bringing in initial conditions and Cauchy development, just diagnostic of the space-time itself, that if it has some subset, if its compactified version has a subset O tilde with these properties, that it is globally hyperbolic and it contains the exterior, in fact its closure, then we don't have any naked singularity. However, it's important to note that this does not rule out naked singularity on the horizon. Horizon can still be singular. So under this, so the horizon is defined as H. So it's strictly the region outside the horizon, which is what we call the exterior. Okay. Good. Now we are in position to prove two important theorems, at least one of which I can definitely do now. Before we prove it, there is one little lemma. J minus of square plus is actually compact. Is an open, whatever I'm saying. It's an open set. Yeah. Why is that true? Well, there's an intuitive reason for that. In an open set, if I have a point contained in an open set, then the definition says that a neighborhood of that point is contained in the open set. So here, this thing is, so suppose there's a causal path reaching square plus, then there will always be a neighboring path which is also causal, reaching square plus. It's pretty much in the nature of causality that if I have something causal, there will be a neighboring path to it, which is still causal. And this is like an intuitive proof of this little result, but Wald has a more detailed proof if you're interested. So J minus of I square plus is compact, and sorry, is open. I keep saying compact, I'm sorry. It's open, but then the complement of an open set is closed. Again, its definition. But what is the complement of J minus of sky plus is just the black hole region, so B is closed. And this gets used repeatedly in various theorems. Okay, and now we have all the information we need to state and prove the theorem about black hole splitting, or rather not splitting. So let M with metric G be asymptotically locally predictable. Sorry, not asymptotic. Strongly asymptotically predictable. Okay. And let's take two Cauchy surfaces. Sigma 1 and sigma 2. I'll write the theorem, then I'll draw a picture which will make it very clear. And let sigma 2 be in the future. Any two Cauchy surfaces always have one in the time-like future of the other. So sigma 2 is the one in the chronological future. Now, what we'll do is consider the black hole region intersecting sigma 1 and the black hole region intersecting sigma 2. Remember that Cauchy surface is basically a definition of what time it is. So sigma 1 is at some time t1 and sigma 2 is at another time. So these are like snapshots of the black hole region at time t1 and time t2. So if you like, it's purely the spatial region. It's that fixed time region at T1 and T2. And now, supposing that this black hole is actually a thing that we might call multiple black holes. The space-time, for example, could be our world, which has millions or billions of black holes. So then at a Cauchy slice, this intersection will be the union of many components, which I'm going to call AI, such that each AI is connected. So the AIs are all connected. So it's a disjoint union of connected spaces. And how many can there be? Well, we'll assume that there are n1 different connected components to this at the initial time. And similarly, for the later time, we'll assume that there are n2 connected components Bj. So that pictorially, you can think of this as sigma 2 at a later time, this as sigma 1 at an earlier time, and then here I have these A1, A2, A2, etc. And here I have B1, B2, etc. Sorry?
Can we try to draw this in a Penrose diagram?
I suppose we can by Penrose diagram, but of what space-time? This is a very abstract space-time, so right away we don't. Yeah.
No, M is still asymptotically flat.
Yeah, M is asymptotically flat. That's true.
Okay. No, because I was having trouble imagining sigma 1, sigma 2, the Cauchy slices, because the asymptotic time coordinate is not a time-like coordinate in the black hole region.
Yes, that is true.
So I cannot choose the Cauchy slices to be just constant.
Hmm.
asymptotic.
Yeah, I see that. Yeah, but as long as, so probably since the space is strongly asymptotically predictable, I am presumably working inside this O tilde, and O tilde is assumed to be globally hyperbolic. That is, so what you might be asking is, in Schwarzschild solution, can we see how there is a space, or why is Schwarzschild solution asymptotically locally predictable?
Yes.
What is the globally hyperbolic? So I'll try to get a better pictorial description maybe tomorrow. I don't have one right now that comes to mind, unless somebody can suggest it. But indeed, a Cauchy hypersurface, the point is that inside, obviously there is space and time get interchanged because they pass through a null direction. But there will still be a surface which all you want is the surface should be space-like and achronal. And that still exists inside and outside. And I think because it goes through a null direction on the horizon, I think the surface is not difficult to draw. It doesn't have to be, it's not like the surface has to come in along a fixed time and go suddenly up to a fixed time. It just has to be everywhere space-like. That it can be. I don't think that's an issue. But let me see if I can draw something more convincing tomorrow. So good. So this is the picture. And now the nice thing is, imagine the light rays that pass through. Okay. So, well, just imagine. Okay. So let me state the theorem. I didn't finish stating it. Then, so this is the situation. Then, n2, the number of components here. So this is up to b n2 and this is up to a n1. So n2 is less than or equal to n1. So there are less than or the same number of black holes in the future. And J plus of any of this AI is fully contained in Bj for some j. Okay. So the geodesics coming out from here, for example from A1, can all go through B1, or they can all go through B2 or all go through B3. They don't have a choice that some of them go through B1 and some of them go through B2. Okay, and if they did, then the black hole would have split, because in its future evolution there would be two parts. Okay, so this is what the theorem says, and in particular it rules out splitting, but it doesn't rule out joining, because it could be that J plus of A1 is in B1 and J plus of A2 is also in B1. That's allowed. And we'll see in a moment what is the, first we'll prove the theorem. That already will tell you what is the underlying reasoning. And then we'll see why it's not weird that in one direction, that is a black hole can join, two black holes can join, but one black hole cannot split. It's very intuitively mind-boggling, and we'll see exactly what's going on. So first of all, intuitive proof is the following. Light rays so actually it's best to consider these lines I've drawn to be light rays, and yeah, so light rays must remain from any black hole region from B, remain in B. We've already argued that. Therefore, let's simplify our discussion and just put two black holes here, A1 and A2, and let's consider the bundle of null geodesics coming out from each of them. When I say coming out, I mean coming out of the Cauchy hypersurface. They are not coming out of the black hole. That's precisely what they are not allowed to do. Okay. So now, in the future, we have some connected components. Okay. Suppose the weird thing happens. Suppose the black hole splits, A1 splits, and this is B1 and this is B2. Then some of the light rays have gone in here, and some of the light rays have gone in there. Okay, that's what must happen if it splits. But no light ray can go here, because if it goes here, that means it passes through the next Cauchy surface in the exterior of all the black holes, then it's going to reach infinity. But that's a contradiction, because it came out from the black hole region and it reached square plus. Not supposed to do that. Okay. So the intuitive idea is that if this is going to happen, then all light rays have to choose when they come out of A1 whether they are going into B1 or into B2. So there's like a sharp division, and I'll be able to show that the light cone itself is not connected. There's a break in the light cone. It's not continuous. Okay, so it will violate continuity. If you can have light rays from A1 going to B1 and B2, it violates continuity of the light cone. That's the intuitive statement. Let's write it more precisely. We'll do the proofs properly. I would always encourage you to go and read both Wald's and Witten's proofs. You'll find one is more precise and more rigorous than what I am saying, and the other is less rigorous, but it's equally, I suppose it's equally precise, but it's more based on words. So, good. Okay. So actually the rigorous proof is not terribly different from what I wrote. So let's focus on A1. So start with A1. So A1 is one of the connected regions at the initial time, and since A1 is in the black hole region, so it's in the intersection of black hole region with the Cauchy surface. So it must also be that the future of A1, the causal future, is also in the black hole region. This is the statement follows from what we said earlier, that the future, causal future of any point which is in the black hole must remain in the black hole. So this has to be true. Okay. Therefore, J plus of A1 intersection sigma 2, causal future of A1 over there, whatever the image of this over there is, must lie in B intersection sigma 2. Sigma 2 is the future Cauchy surface. So this establishes the fact that light rays coming out of A1 must necessarily go through sigma 2. Now, if J plus of A1 intersection sigma 2, this thing, is connected, then we are done. Because if it's a connected region inside sigma 2, then it must be lying inside one of those B1, B2, B3, because those are all the connected subregions of the black hole region intersection sigma 2, right? So any connected black hole region lying intersecting with sigma 2 has to be inside one of those. It could coincide with it, or it could be smaller, but has to be fully inside. So then we are done, because it means that the causal future of this A1 is lying inside, say, B1 or B2, one of them. So we are done. So all we have to do is prove that J plus A1 intersection sigma 2 is connected. Well, as usual, we pull out our favorite trick, assume the contrary, that it's disconnected. Okay. So in that case, there are two non-trivial open sets. Non-trivial means non-empty actually. Open sets O1 and O2, both of which are in J plus A1 intersection sigma 2. If it's disconnected, then there must be two non-empty disjoint open sets in this. Okay. Now let's look at so let's draw those open sets. So right now we don't know what are the B's. This is sigma 2. There are some B's, B1, B2, B3, which are the connected regions. I'm ignoring what they are because I'm focusing on the future of A1 on sigma 1. So what I'm going to do is draw O1 and O2. Since the future of A1 is said to be disconnected, there is an O1 and O2 such that A1 lies in the past of both of them. But let me pick a particular point, P, inside A1, such that P is in J minus of O1 intersection sigma 1. In other words, there is in the past of O1, P lies in the past of O1 basically. Of course, intersection sigma 1 because P is already chosen to lie on sigma 1. So there's a light ray going there from O1. So the question we want to ask is, can P also lie in J minus of O2 intersection sigma 1, yes or no? Okay. So again we'll assume yes and then we'll see that's not possible. If yes, then the future directed null geodesics emerging from P is actually, I almost feel bad to write this proof because it's saying nothing more than what I said right from the beginning, but still, all this looks nice to be formal. Emerging from P, enter O1 or O2, which are disjoint. So the future directed null geodesics coming out from P. So in this scenario, if yes, then the scenario is like this: that P itself lies in the past of O1 and O2. Okay, so there's a null geodesic going out from P, which goes here, and there's another null geodesic going out from P, which goes there. Okay. And this allows us to split the light cone into two components. By light cone here I mean the interior of the light cone. At P into disjoint components. And this is not possible. I don't remember if I gave a precise statement about light cones being connected when we discussed light cones. If I didn't, then let me think what the precise statement is, but I think the verbal statement is that light cones are connected. It should be simple to show. Okay, so this is a contradiction, but the contradiction came by assuming yes over here, that P is in the past of both O1 and O2, therefore P is not in the past of O2. Therefore P is only in the past of J minus of O1. Now let's repeat this for all the points P in the past of J minus of O1 on the surface sigma 1. Okay, so we repeat and we get a set of P in J minus of O1 which are not in J minus of O2. Okay? But now, supposing there's another point P prime, similarly we can get a set of points P prime in J minus of O2. But so this is not in J minus of O1, and these are not in J minus of O2 by symmetry. Right? So in this way, we have split A1, which we started with, into the points in J minus of O1 and the points in J minus of O2, and these will be disjoint sets. So A1 splits into disjoint sets, disjoint open sets. And this is another contradiction because A1 was one of the connected components of the original black hole region. Okay, so this proves that J plus of A1 intersection sigma 2 is connected, and that's all we wanted to prove. So frankly, when I first heard this theorem, I was a little baffled by which part of the theorem is violated if I go in the other way, because it looks like I've just shown that this can only be, light rays from this can either go all into this or all into that. But surely two black holes can merge, and we are completely sure that this does happen. And in this case, light rays from both go in there. Why doesn't this split the past light cone of that? Okay, and the simple answer is that there are also light rays which can go into that black hole in the process of its formation, which aren't coming from either of the two black holes which are merging, but from outside. From the outside, they are perfectly entitled to directly enter this black hole without ever having entered these. This is exactly the one-way nature of the black hole horizon. Light rays can surely enter from outside, but here they can't leave this way into the exterior, otherwise they would reach scry plus and they wouldn't be in the black hole region. These ones are coming from scry minus, and they'll enter the black hole here. And now you see that the bundle of light rays entering this is completely connected. Some are coming from here, some are coming from here, some are coming from the exterior, and so it's perfectly possible for that whole thing to be connected. That's the crucial reason why so black holes can join. The black holes can't split. Okay, I think this is a reasonable point to stop. Yes.
I thought it would be important to somehow use the fact that there is a future trapped surface.
No, I don't think so, because we are not saying anything about whether the black holes do. We are only ruling out something, right?
No, because that is where we are putting in we are breaking time or something by saying that it is future trapped.
No, I would have not said that. I think the point. No, I think the trapped surface is. The trapped surface arises once a black hole is formed, and it's more a statement about the singularity, but we are not even using the singularity here. Singularity is not really playing a role, except, okay, that we started with an strongly asymptotically predictable space, so there's no external singularity, but the singularity inside the black hole is not playing a role in this discussion. It's simply the one-way nature of the horizon which is playing a role. The fact that light rays going out to the future from the interior of a black hole they are forced by the definitions we have given to always remain in the interior of the black hole. That means that when it splits, if it splits, they have to choose discontinuously which of these they go into. That's all that's coming. So only the causal structure at the horizon. And of course, you might have said, well, in that case, they'll also choose that few of them go out. That's what cannot happen. So they are forced to choose only one by continuation. Yeah, it doesn't really rely on trapped surfaces, but the next result does. The next result, which I'll do tomorrow, says that if I have a strongly asymptotically predictable space-time satisfying the null energy condition, so there is now a condition, then it contains a trapped surface. And I think as a corollary, you can show that there cannot be a trapped surface which is either partly outside the black hole region or fully outside the black hole region in a strongly asymptotically predictable space-time. I mean, practically the definition of strongly asymptotically predictable has been rigged exactly to prevent that happening. But this is nice to, so sorry, I read the statement wrong. If the space-time is strongly asymptotically predictable and if it contains a trapped surface, then that surface is fully inside B, the black hole region. That's the statement. I don't know why I read that it contains a trapped surface. So, trapped surface must be fully inside. It can't be partly inside and partly outside, nor it can be fully outside. And it's relatively easy to prove, but I'll do it tomorrow. And again, Wald has a formal proof. And once we do that, then we are set to do Hawking's area theorem, which is that in any physical process, the area of a black hole will increase. And of course, this is one possible physical process, joining of black holes, but of course there are others like throwing things into black holes. Good. Anything, any questions?